Class 11th Chemistry, Unit 7 Equilibrium, and in this video we will discuss about homogeneous and heterogeneous equilibria. First come to homogeneous equilibria. In a homogeneous system, all the reactants and products are in the same phase. For example, this is manufacture of ammonia by nitrogen and hydrogen, and in this reaction, reactants are in the gaseous phase and product is also in the gaseous phase. That's why this is homogeneous equilibrium. Another example, this is hydrolysis of an ester CH3COOC2H5, and we are taking its aqueous solution, means solution in water. Okay, and when this is hydrolyzed water, this is also in the liquid, it forms CH3COOH in aqueous, C2H5OH aqueous. Okay. One more example, this is Fe3 plus aqueous, SCN minus thiocyanate ion aqueous, and this will form FeSCN2 plus aqueous. Reactants and products are in the aqueous form. That's why this is the example of homogeneous equilibrium. Now, equilibrium constant in gaseous systems. For reactions involving gases, it is usually more convenient to express the equilibrium constant in terms of partial pressure, and equilibrium constant is represented as Kp. Actually, we already discussed about this is Kc. Okay, Kc and Kp both are the equilibrium constant. Okay, when concentrations of reactants and products are expressed in terms of mole per liter, that is in molarity, then we use the Kc. But when gases are involved, this is convenient to express the gases in terms of partial pressure. Then we use the Kp. Okay. The relation between Kp and Kc we will discuss in the next video. Heterogeneous equilibria. Equilibrium in a system having more than one phase is called heterogeneous equilibrium. For example, this is H2O in the liquid state is with equilibrium with H2O in gaseous phase. This is liquid and this is gas. More than one phase is there. Okay. One more example. This is CaOH twice in the solid state. When this is dissolved in the water. Okay. Actually, this is partially soluble in water. That's why this will dissociate to give Ca2 plus aqueous and 2OH minus aqueous. Okay. Again, this is solid, this is aqueous, this is aqueous. Different phases are there. That's why this is the example of heterogeneous equilibrium. Heterogeneous equilibria often involve pure solids or liquids. Molar concentration of a pure solid or liquid is constant, that is independent of the amount present. Remember, important point is there. Molar concentration of pure solid or liquid is constant, whatever the amount present. In other words, if a substance X is involved, then this represents the concentration of X in solid state. This is XL. This represents the concentration of X in liquid state, and both these concentrations are taken as constant, whatever the amount of X is taken. While if this X in gaseous form or X in aqueous form, then this represents the concentration of X in gaseous state, and this represents the concentration of X in aqueous form will vary as the amount of X in a given volume varies. Yeah, simply we can say when we write the expression for equilibrium constant, concentration of pure solids and liquids is taken as constant. Okay, and we will not involve these terms in that expression. For example, thermal dissociation of calcium carbonate, CaCO3. This is the symbol for heat, that is thermal, and this will form CaO solid and CO2 gas. This is one reversible reaction. When we write the Kc on the basis of stoichiometry equation, then this is in the numerator we will write the concentrations of products. Okay, and in the denominator we will write the concentration of reactants. But this concentration of CaCO3 solid and concentration of CaO solid are both constant. That's why we will ignore these terms and we will write the equilibrium constant equation like this. K dash C is CO2 gas, that is concentration of carbon dioxide in gaseous form. Okay. And if this concentration expressed in terms of partial pressure, then we can write Kp is equal to partial pressure of CO2. Take one more example. This is Ni solid plus 4CO converting into NiCO4. Actually, this reaction is used in the purification of nickel. Okay. Now, in this case, this is solid. That's why we will not write this term in the equilibrium equation. So, we can write Kc is equal to concentration of NiCO4 divided by concentration of CO power 4. Why this is 4? Because this 4 is the stoichiometric coefficient of this CO. This is one more example. Ag2O solid plus 2HNO3 aqueous converting into 2AgNO3 aqueous plus H2O liquid. Now again, this is solid and this water is liquid. We will not mention the concentration of these two substances in equilibrium constant expression. So, Kc is equal to concentration of AgNO3 power 2 divided by concentration of HNO3 power 2. Okay. For the existence of heterogeneous equilibrium, pure solids or liquids must also be present at equilibrium, but their concentrations or partial pressures do not appear in the expression of the equilibrium constant. Okay, thank you.